Electrons escaping atoms. Learn how a powerful electric field can turn the Stark effect into a wild quantum jailbreak. Here is a picture of the Stark effect, which seems to be splitting the energy levels thanks to the electric field. And doesn't this look familiar? It actually is the cousin to the Zeeman effect, which we saw back in chapter 7, where this effect was first mentioned. So, if it works for magnetic fields, it also works for electric fields, but we'll keep that for a later discussion. The problem today that we have is problem 9.18. So, tunneling and the Stark effect. When you turn on an external electric field, the electron in an atom can, in principle, tunnel out, ionizing the atom. So the question is this likely to happen in a typical Stark effect experiment? Can we estimate the probability using a crude one-dimensional model as follows? Imagine a particle in a very deep infinite square well from section 2.6. Part A, what is the energy of the ground state measured up from the bottom of the well? Assume that V0 is much greater than h bar squared over ma squared. This will become very important here soon. And the hint is, this is just the ground state energy of an infinite square well of width 2a. Cool, we can deal with that. Now, introduce the perturbation h prime equal to negative alpha x. For an electron in an electric field E equals negative E external in the I hat direction, we would have alpha equal E to the external times the external field. Assume it is relatively weak such that alpha A is much less than h bar squared over ma squared. This is how perturbation theory works, so has to be a small effect. Sketch the total potential and note that the particle now can tunnel out in the direction of the positive z or positive x-axis. Calculate the tunneling factor gamma from equation 9.23 and estimate the time it would take for the particle to escape from equation 9.29. The answer is given here. Now we need to prove it. Put in some reasonable numbers, such as V0 equal 20 electron volts, the typical binding energy for an outer electron, A equal 10 to the negative 10 meters, the typical atomic radius. The external field is 10 to the 7 times 10 to the 6 voltmeter. Strong laboratory field. Well, yeah, definitely strong. E and M are the charge and mass of an electron. And calculate tau and compare it to the age of the universe. So this is going to be fun. Okay? Why do we care? Well, we care because it's the Stark effect, the cousin to the Zeeman effect. Both effects we saw had very big changes in what we thought we knew about energies and what would be allowed under measurements. And because we use the electronics in measurements, the Stark effect definitely has a role. That being said, the challenge I have is which effect is more significant? We clearly saw how much of a disturbance the magnetic field has. Now we're dealing with the same concept with the electric field, but which one, in your opinion, is more significant to the theory and actual quantum measurements? Let's not forget that the PDF is still available, although it's weird linking. I set it up for the Patreon for all the members, free of course to join. And if you want it, I can send the link to your comment. Just comment PDF and I can send it to you. If it is not in the description, you can definitely have access to it. No problems there. If you find value in this content, you can have a direct impact on its success by liking, subscribing, sharing with a friend, or donating through Buy Me a Coffee. No account required. So with that, let's jump into this question. All right. So stop number 1 then, we have part A. The infinite square well energy can easily be modified. Noting that the infinite square well energy for any level n was n squared pi squared h bar squared 2ma squared. They told us this was the same energy, we just need to put the width at 2a. So a to 2a, and now we see that we have a square on the 2 and the a, so we get a factor of 4. 2 and 4 make 8. Notice that we were asked for the ground state, so we would have to plug in 1 for n n squared is just 1, so we get our ground state energy, so we're good to go. Nothing terrible there. Now, to put the potential into the normal form that we see, well, we saw that the potential here, we had V0, which is some negative number, between negative A and A, and so we're fine there, but the perturbation now affects us to where we have this minus alpha x term here. So let's go ahead and take a look at what we have for our diagrams. Now, I had made some pictures in Python that just weren't quite as elucidative as this because Python wants numbers, so the book had plenty of offering here. Um, Here we see that the potential V of x, we shove everything down to the negative since we're dealing in negative energy, so negative 13.6 eV, things like that for the Bohr energy. Nothing too crazy, but I'd like to point out here how it's nice symmetric well. The E1 was the difference between the bottom of the well and some energy level. So we're measuring E1 from the bottom of the well, not from where we had it at the axis. Because remember in chapter 2, we put the bottom of the well on the x-axis, so that's where it's measuring from. So if we're going from V0 equals something really small, we're measuring up until we get to 0. So that's what we're trying to do here. Now, when we introduce the perturbation, with the fact that it's a linear, we have a negative skewed line here, a negative linear line here, and here. They are going to connect. But because we have a shift from A to negative A to A, we shove it down. And we see that E is the line that we're looking at, where we could have possible tunneling some later point due to this turning point. And again, E1 is between the bottom of the well and this level. That being said, this is going to cause problems in the nomenclature, so to speak, when we're looking at what is the potential, what is the energy of the system, and how do we find a turning point. So just keep this picture in mind that we're going to have to overcome this barrier here, which is E1 and V together, and then E here is just acting as the energy, and then we can manipulate it how we see fit in due time. Notice now that the potential varies with position, and thus is perfect for the WKB method. Of course, since E is less than V in this case, because it's higher up, we know that this is a non-classical region, so we can deal with tunneling. Alright, so before we can do anything else in this regime, what we have to understand is that we first need to determine the turning point of the system before we can address the tunneling integral. So remember that this happened when E is equal to V of x. Now here, this is our potential that we're looking at, okay? We had enough negative signs on all of them that we just canceled. And in the PDF, there's all the little nitty gritty as normal. But with that being negative, and we're looking at the difference between the well bottom and the line E, as we saw in the last picture, that vertical line between the dash lines and the bottom of the well, this turns into the energy that we have to overcome. So V0 minus E1, okay, we can deal with that. So solving for x0 is just dividing by alpha, so we're good to go. And a little bit of hindsight and future proofing for the question, it behooves us now to go ahead and solve for what E1 is here, which is V0 minus alpha x0. So we're good to go here. Just keep in mind you're not going to have to use this for any time soon, but will be helpful later. So moving on to the momentum of this regime, we see that normally this is E minus Vx, and we're highlighting here specifically that the E term was the difference of the ground state and the potential, and the potential term here that we're looking at is the perturbation for the system, hence the color code. So we go ahead and put E1 minus V0, then minus the negative Vx, which was the perturbation, and the two negatives make a positive, so we're good to go. And if we notice here that E1 is equal to this thing up here, we can plug this in, so we actually didn't wait that long. But we see that the actual potential of the situation cancels in both cases. So that's why we didn't care to reference what the well depth was because of the cancellation effect, and now we're good to go. So because of this, cancel, cancel, we see that both terms have an alpha alpha, so factor that out. And now we see that we have a negative x0 plus x. And let's go ahead and do some more manipulating of this before we take into account the integral. Okay, so what we do here is because x is some later point beyond the turning point, we want to factor out a negative out of both of these. So because there was a positive on the x, that turns it to a negative. And that negative sign here turns it to an I. But remember, since we're in the non-classical region, we need the magnitude of the momentum. And that I turns into a 1 because magnitude of I is just a distance of 1. So we're fine. And then we have 2m alpha and then x naught minus x. Noticing that the x naught was some further point right than where x is going to be in our jurisdiction. So we want to have that negative sign there so we're not having any sign problems later. And so now we can look at the tunneling factor for the exponential gamma, and that can be evaluated by using our famous formula now. Noticing that 2m alpha is a constant with respect to x, so we just take that outside immediately. And then A was the edge, the right edge of the well. X naught was some turning point later, and hence we have x naught minus x inside. Again, this is all to be to the square root, so we just put it to the 1 power now. And what we immediately see is that upon a u sub, we can simplify this down very quickly. And so we see that u equals x naught minus x. Solving for x, we get x naught minus u, so dx would equal negative du. But let's go ahead and evaluate the limits so we don't have to deal with them later. The upper limit, which is at x naught, plug that in. We substitute that in there. We see that we get a cancellation, so that goes to 0. Woo, we like that. Now we have u of a. Well, if that's the case, we get x naught minus a. But we know that x naught is some further point right. But we also saw that the turning point is what we solved for in the initial part of section 3. So that was x naught minus v1 over alpha. Not bad in and of itself, but now we need to take into account this minus a here. So to do that, we had to find a common denominator, and hence the a and alpha here. So now that we have our new limits, we can evaluate this integral pretty quickly. All right, so now the gamma integral, or the tunneling factor, is 0 to our second point here, which has the turning energy and all the other fun stuff. But notice that we could switch these limits at the cost of a negative sign, so we're good to go. This just 1/2, so add 1 to the power, divide by the new power, evaluate at the bounds, multiply by the reciprocal of this fraction here, so the color coordination works. And now you see that we get a 0 on the right boundary, so we're fine. Or I guess the left boundary technically. And now we're just left with this mumbo jumbo over 3/2 power to simplify. And in order to simplify this, let's go ahead and put this 2 into the square root just to get rid of it. And we'll see if that simplifies down later. But what we see here is that we're told specifically that the perturbation is weak. So alpha A is much less than h bar squared over ma squared, which we saw was approximately equal to the ground state. So we see that the ground state is much less than, or excuse me, is greater than the alpha A, so the perturbation of the Stark effect. But we're also told in part A that V0 was much greater than E1. So in total, we see that alpha A is much less than V0, and E is much less than V0 too. So that's cool. Both the alpha A and E1 terms being so much smaller than the potential V0, they don't take away much from the potential that is here. So we see a negative sign. So they're subtracting off very little, and so we just throw them out in this approximation. They're not going to lead to much, especially in the square root and cube that we have here. So this gamma factor now simplifies to this, where we just have a V0 up here to the 3/2 power instead of the E1 and a alpha. And that 2 squared turned to a 4. Multiply the 4 and 2, we get an 8. We turn this 3/2 power into a square root with each term cubed. That way we can join this square root and that square root together into this thing here. Noticing that 3h bar has nothing to do with the square root, so it just chills outside. The factor of alpha in the numerator cancels with 1 in the denominator, hence we get a square there. But then noticing that we have a square in the denominator and a square root, that can come outside. So we finally get the gamma or tunneling factor figured out, and we replicate the results that were given, which was 8m v0 cubed over 3 alpha h bar. So good to go on all accounts there. Now, in order to estimate the tunneling time from equation 9.29, we need the velocity. And we could find this via the energy equation, where we have the kinetic energy over here with the ground state energy here. This 1/2 would have to be multiplied over, so it just cancels with the factor of 2 and the 8, turning it to a 4. This m would have to be divided, so that turns this m into a square. Now, noticing that every one of these terms is a square of some sort, we see that we get pi h bar 2ma all squared, so we're perfectly good to go. And that leads us to v equal pi h bar over 2ma. Not bad at all. Again, we saw this trick with the alpha particle, and that's what we're going to have to keep using time and time again. So nothing too outrageous, but be aware, old tricks definitely keep us happy. Now, the tunneling time, tau, was 4a over v, so we just plug in the v that we just found, with the exponential times 2 gamma, but the gamma we found was up here, so we're good to go. Noticing that we're dividing by a fraction, we multiply by the reciprocal, so the 2 and 4 turn into an 8. This a and this a turn into an a squared. So we see that we get 8ma squared over pi h bar, with e to the 2 times everything that we saw from the tunneling factor, except the alpha term now gets substituted in as e times the external electric field. And to make our computations easier, we have a coefficient term and then the tunneling term. And trust me, trying to plug all these in will be tedious, so let's get to it. Alright, so part D. Now the numeric side of the calculation. Well, the coefficient that we see here, when we plug in the mass of the electron, which is the 9.11, 10 to the negative 31, the A, which was just the radius that we saw in a typical atom, we see that we have the Planck's constant here. All of that in a calculator gets to a lot of decimals here that I shortcut it to 2.2, and then we see that we have 10 to the negative 16. The tunneling factor here, well, we had 8m, so the mass of the electron, and then we had 20 eV, but we have to turn this into volts due to the electric field being measured in volt per meter, excuse me. So we have 20 for the electrons, and then the charge of an electron. Okay, so that's where we get those numbers. Now that alpha turned into E times the external magnetic field, so the charge of E is just 1.6 times 10 to the negative 19. The magnetic or the electric field was 7 times 10 to the 6. Planck's constant again. And all that comes out to a lot of decimals, and we shorthand that to 4.4 times 10 to the 4. Again, all the decimals are in the PDF. And when we put this together with the tunneling time, we get this expression. And that's pretty cool, pretty happy, no big deal. But I challenge you to plug this into a calculator because what you're going to get is an overflow error. So what you have to do is go back into something like Mathematica or a computational engine, and they'll be able to handle this crazy amount of significant figures, or not sig figs, but this a crazy exponent here. So that's 2.7 times 10 to the large number of 37890. That's in seconds though, and even if we converted this to years, that would be 8.6 times 10 to the 37882 because it was like something times 10 to the 7 seconds per year. And that's an absurdly large number. Like, it is catastrophically big. The age of the universe, according to Google, is about 13.7 billion years. So if we convert that to scientific notation, we see that we get 1.38 times 10 to the 10 years. Um, so that's a dramatically different amount of number right there. There's no way possible to conceive how large this number is for the tunneling time. So what this tells us is that this number is huge and the likelihood of tunneling is nearly non-existent. Clearly, this would be a great insert for a meme, so you're telling me there's a chance, but it doesn't actually seem to come to fruition in this case, so clearly nothing to worry about. But wow, what a big number. Whew. Alright, so in summary, you got to see the cousin to the Zeeman effect known as the Stark effect. That's pretty cool. And a whole lot of manipulation with the approximations, what's larger, what's smaller, and how that plays into things, where they play into things, the effects that a perturbation can have on the potential, and what that potential can therefore be analyzed, what tools can use to analyze it. So very, very nice to see. Again, I have to give a massive thank you to all my supporters for making this possible. I'm extremely grateful for all your support. None of this would be possible without you and the continued support you give. So thank you, thank you, thank you. If you'd like to see more, you too can become a patron for access to the supplemental material, current and future projects, and of course, one-on-one help now that the new semester is here and rolling strong. New content is posted weekly to help fuel your curiosities. Books, notes, and other reference materials are found below, or if not, I will link them to you somehow. If you have any questions, please feel free to reach out. Learning is not a one-dimensional task. It takes several perspectives to help you gain the insights you need, whether it's for a class or for whatever seems to be bugging you in your own research. Always, always, always feel free to ask questions. As always, thank you for watching, and until next time, stay curious.